see everyone here in person, the vast crowds that we're having here today. Looks like that better. Audio seems a little quiet, but hopefully that's a little bit better here. Changes a little bit every day. So if you're joining me online, please just let me know what you think the audio sounds like always when we first start, and we'll move forward from here. So we are in the unit on global warming. We will complete that today. We got a little bit more than halfway through last class, and we talked about, I guess, the evidence that global warming is real and happening, and we talked about the chemical reasons behind global warming, and in particular, we talked about, for global warming, we talked about how if you have a molecule that has polar bonds, where the polarity of the bond changes during a vibration, that is necessary in order for a molecule to absorb infrared light. And we looked at carbon dioxide, and we looked at the types of bonds it has, that they're polar, and they can, the polarity of the molecule changes through the course of the asymmetric vibration. And then we talked about, of course, how that can cause carbon dioxide to absorb infrared light. And other molecules we looked at did not absorb infrared light, including nitrogen, N2, oxygen, O2, because those are always nonpolar, regardless of whether or not there's a vibration going on. And we also looked at monatomic gases, gases that only have a single atom, and that would be like the noble gases, like argon, helium, neon, whatever. Those would be examples of ones that are also not greenhouse gases. They cannot absorb infrared light. Great. Thank you, online folks, for keeping me up to date with how my audio sounds. Hopefully it stays okay. I don't know why it jumps around every time I start this up. Like, you'd think you'd set the same settings and there'd just be, but I just have to adjust it a little bit. But that's okay. That's no problem. One other thing I'd like to point out is that assignment 2 instructions have been posted. I've been getting some emails, so that's great. I see people are reading that, looking at it, checking it out, and preparing. I also posted on our Acorn page examples of ones from previous years. Some of them are pretty good. They're all pretty good. So check those out, give you a kind of an idea of a couple of things. Those ones that I posted are more on the sort of the better end. And there's some that are on the lazier end for sure as well, that I'm not putting that out as an incentive for you to try to match. So yeah, this will be the year, right? Biggest class I've ever taught for this course. So this will be the year that the best one ever comes, right? You guys have all kinds of time to prepare and get yourself ready. All right, so I'm going to just delete that. Okay. All right, so hopefully my audio didn't really change when I switched this. Okay, so we are talking about mainly CO2, and CO2 is certainly the gas that gets the most airplay when it comes to global warming, because we produce so damn much of it, right? Every time we burn fossil fuels, carbon-based fuels, which is almost all of the fuel we burn, that would be anywhere from wood to coal to oil products, gasoline to natural gas. All of these things are carbon-based compounds that we burn as fuel and end up ultimately as carbon dioxide, which is better than carbon monoxide, but still, we are putting a lot out into the atmosphere. It's building up over the years, and it's absorbing more infrared light, causing less energy to escape the Earth, and therefore it's causing the average temperature of the Earth to go up. So this is part of a big carbon cycle. There's a carbon cycle on the planet where carbon goes into the gas phase as CO2. It's collected by plants. It's turned into solids. It's turned into things like carbohydrates, and it's turned into lignins and other organic molecules. Those end up getting buried and turned into fossil fuels, which we are then bringing back out of the ground. Of course, this is a very slow process. One very important process that causes carbon to exit the cycle is what's called the biological pump, which is shown in this picture right here. This island is Ireland, and you can see in the water this sort of bluish, greenish bloom, I guess, if you will. This is phytoplankton, and what happens is when you have, I guess, nutrients enter waterways, there can be an explosion of photosynthetic life, and those organisms can die. Eventually they will die, and they can either decompose and turn back into CO2, but some fraction of them will die and settle down and go eventually down to the floor of the ocean. They can build up there, they can be covered up by minerals and so on, and they end up turning into sediment. And that's one way that carbon, an important way, that carbon can exit this cycle. So if every human being just died right now, and we stopped all of our burning of fossil fuels and whatever, gradually, very slowly, the carbon dioxide levels will start to come back down through things like this biological pump cycle, as well as trees and so on growing in areas where they're not growing right now. But it would be slow. This is what carbon dioxide levels look like in our atmosphere going back to the 1960s. And notice this red line, I guess running average is that black line. You can see it fluctuates up and down each year. The red line goes up and down and up and down. That's due to winter-summer cycles. And what happens, of course, in the summer is in the northern hemisphere, for sure, you have trees growing again, leaves all come out. They're drawing carbon dioxide out of the air at an increasing rate, so you get a little drop. And then in the winter, when everything dies, everything starts to decompose, and we're, of course, up here burning fuel for transportation and heat and so on. It kind of goes back up. So it kind of oscillates up and down every year with the season. But what you can see definitely since the 1960s is this definite, obvious, long-term trend of increasing carbon dioxide concentrations in the atmosphere, going from about 320 parts per million up to over 400 now. And I remember teaching this course like 10 years ago, let's say 2010, when the concentration of CO2 in the atmosphere was sort of safely under 400 parts per million. And I remember predicting to people using a version of this from the time, version of this graph from the time, what the CO2 level might look like, or what year it might actually hit 400. And when it hits 400, you're going to see it in the news, and et cetera, et cetera. That's in the past now. We've zoomed past 400. I don't know what the next notable milestone is going to be, but from 320 to 400, percentage-wise, is a pretty big increase, right? It's what, 20% or so? So significant. And this is due to decades, of course, of burning fossil fuels, not just cars, but also industry and many other things that create CO2. So this is just a little bit of a zoom in. You can see it's still rising, and there we go. We can actually get carbon dioxide levels in our atmosphere going back many, many, many years. In fact, thousands of years. And the way they do this is they take ice cores, like where you have a glacier, for example. You can drill down into the ice, bring up ice from hundreds or thousands of years ago, and that ice will have in it trapped little air bubbles. And you can remove the air bubbles, and you can actually measure how much CO2 is in the air at that time. So it's like a time capsule showing you carbon dioxide concentrations going all the way back. So we can generate graphs like this. This is showing CO2 levels in the atmosphere going back 10,000 years. And 10,000 years is kind of a significant date, because 10,000 years is when the last ice age ended. And so everything kind of since then is post-ice age, and really human civilization kind of matches up with around that time as well, at least our record of human civilization. So you can see it's been pretty flat, somewhere around, I don't know, 275 or so. And then in the last, let's say, 200 years, it's really shot up. And as you can see from the inset on this graph, this sort of zoomed in area, it's kind of increasing at what appears to be an exponential rate, as has our population. So that kind of goes along with that as well. Going back even further, this is going back hundreds of thousands of years. And what you can see is estimates of CO2 concentrations in the atmosphere follow very strongly estimates of the surface temperature of the Earth. And we know there have been times in our past where the Earth has been a lot warmer, and times, of course, when it was a lot colder, like the last ice age. The Earth does go through natural cycles of increasing and decreasing temperatures. But what you can see in terms of CO2 seems to be correlated to the temperatures that we see on Earth, or that we estimate. Of course, no one was around then to measure them. But the CO2 concentrations we're seeing now are at levels that we haven't seen in over 500,000 years. So dramatic increase. That's that yellow line here, well above any point we've ever seen in our not even recent past. This is showing a plot. The black line here is the CO2 levels. The red lines are temperature anomalies. So we looked before at how the temperature of the Earth has increased or decreased relative to CO2. Very strong correlation here between CO2 increasing as well as the average temperatures increasing. So people are pretty confident, right? If you think of the whole planet as being like a lab experiment where we're trying to definitively link carbon dioxide with these temperature increases. There's so many variables, and we don't have the same control that you could expect to have over like a reaction flask, but everything is telling us that these two are causatively related and that the increase in temperature is a result of this increase in CO2. Of course, where's this CO2 coming from, right? Well, every vehicle, just checking the sound here. Is that a little bit better? A little bit quieter maybe, but maybe hopefully a bit clearer. When we drive vehicles that burn carbon dioxide, and not just drive them, but anytime we consume anything, food, whatever, that was shipped here in a vehicle that burns any kind of fossil fuel, that's creating more CO2, which is going out into the atmosphere. And this has been sort of the backbone of our economy for well over 100 years. Not just transportation, shipping, production. Anytime we burn fuel for electricity, all these sorts of things, right? When we turn on the lights, when we turn on the air conditioning, turn on electric heat, this is all burning fossil fuels, which contributes to CO2. Now, I shouldn't say all. There's other sources of electricity as well besides burning fossil fuels. In Nova Scotia, I believe it's around half of our electricity comes from burning coal. But you can get electricity also from nuclear, which doesn't produce carbon dioxide, or hydroelectric, or solar, or wind, or any number of other sources as well. This is showing global CO2 emissions by region up to 2015. You can see definitely since 1950, the lion's share of the carbon dioxide that has been emitted by human beings has happened. So it's sort of a fairly recent thing, meaning sort of one human lifetime. Within the last one human lifetime is when you're seeing all of this emissions take place. And you can see which countries are emitting which. And you can see, at least in the US and the EU, the blue and the yellow, in recent years, there's been actually a bit of a dip. There's been a decrease in CO2 emissions in these countries, but these have been more than offset by increases in developing nations like China and India. And one thing as well that we've noticed in our economy is an outsourcing of pollution. So while it looks like the EU and the United States have really cleaned up their act, and everyone else should do the same thing, what's actually happened is that much of the most polluting industries have been transported to China. And so emissions that result from consumption in the EU and the US are being emitted in China for legal reasons, because of regulations, because of financial incentives, and so on. So it's not really necessarily China's fault. It's still consumption in the Western nations that are driving a lot of that pollution in other countries. Question: how can we know what CO2 levels were hundreds of years ago? By taking air samples from high up in the stratosphere where the air is older. People actually have been taking them since ancient Greek times, extrapolation backwards from modern data, or by obtaining old air samples trapped in ice. So the answer to this one is, of course, D, or whatever the letter happens to be in your own personal version of this quiz. CO2 is not the only factor. There are other gases as well that are considered greenhouse gases. In fact, lots of other gases. Water is a big one. We have lots of water in our atmosphere, except water is sort of a natural and necessary part of our atmosphere, which is going to be there whether human beings are here or not. So we don't really talk too much about water vapors as a greenhouse gas, even though it is. But the number 2 gas that we do talk about and we do worry about that is responsible for this enhanced greenhouse effect is methane gas. Methane gas has the structure CH4, 1 carbon, 4 hydrogens. It's, I guess, arguably the simplest organic compound. It's the smallest, the fewest atoms. And it's believed to be responsible for around 21% of the enhanced greenhouse effect, with around like 78% being due to carbon dioxide. So methane gas actually goes by a number of different names. Sometimes it's called natural gas. Sometimes it's called marsh gas, and we'll see why in a minute. But its systematic name is methane, and it's CH4. So where does it come from? Wetlands actually produce around 120 megatons a year of methane gas. So methane is a natural part of nature. Natural part of nature. Does that make sense? You know what I mean. It comes from when you have organic material that is decomposing with a real lack of oxygen. So you see this in stagnant sitting water when you have dead leaves and whatever sitting on the bottom, and the water is very oxygen poor because it's still, it's not moving, it's not mixing air into it. The decomposition that can happen at the bottom is what we call anaerobic decomposition. That can produce methane gas, which bubbles up. And if you go to a wetland on a warm day and just look at the water, you'll see these big bubbles appear at the bottom and just kind of almost like it's boiling extremely slowly and kind of bubble up to the surface. And that's part of a natural system. And in fact, human beings probably are reducing the amount of wetlands we have, so our human activity is probably reducing methane from this particular source. Termites actually produce in their guts methane gas. We see this in organisms that can eat and digest cellulose. And what normally happens with these organisms is they don't actually digest the cellulose themselves. They have I believe it's a symbiotic relationship with bacteria in their gut, and that bacteria also produces methane gas. So termites, by eating wood, which contains a lot of cellulose, are producing some significant amount, 20 megatons of methane into our atmosphere per year. If you do the same thing with methane, though, that we did with carbon dioxide, what you can see is that atmospheric methane levels have also dramatically risen in the last 100, 200 years, along with carbon dioxide gas. So that means there must be other sources of methane that are human-derived, that are not naturally occurring. This is not part of some natural cycle. So garbage dumps actually produce 40 megatons a year. So our garbage dumps produce twice as much methane gas as termites. And that's because garbage dumps contain a lot of organic material. That organic material gets buried. It decomposes without access to oxygen, so it decomposes anaerobically, produces methane, and it comes up. One of the best ways that you can prevent methane gas from your own personal garbage that you produce is to compost. This is one of the main drives behind composting programs, because what it does is it takes away the organic material that would be otherwise turned into methane And when you compost it, you get, first of all, material you can use to enrich soil, but a lot of the decomposition produces carbon dioxide, which is actually a lot better for the atmosphere than methane gas is. And we'll see why in a little bit. So this is definitely a human-caused problem, not a naturally occurring problem. Rice paddies. This is a nice aerial photo of rice farming. And in rice farming, the way that it's often done is the land, if it's got any kind of hills or anything like that, it's terraced, and these flat areas are created, and they're flooded, and rice is grown in that flooded region. So what you're looking at here, each of these sort of areas is a flat region that's flooded that you could then grow rice in. And it turns out rice doesn't naturally grow in flooded areas like this, but it can tolerate flooded areas like this. So the reason we grow them in flooded areas is because most other plants will not tolerate flooding like this. So that means we can grow rice with very low use of pesticides or anything like that, herbicides, because the flooding effectively gets rid of weeds and so on. But again, you have standing, stagnant water here. You can have organic material underneath without access to oxygen undergoing decomposition. 60 megatons, so rice farming produces twice as much, 3 times as much methane as termites, 1.5 times as much as the garbage dumps. Cattle. Now cattle, you could argue, are naturally occurring organisms, but certainly the populations of cattle that we have right now are nowhere near what the natural populations would be if it weren't for human activity. Of course, we cultivate large populations of ruminant animals like cattle for meat and for milk and for leather and for other things as well. Cattle are another sort of animal that can digest cellulose, not with enzymes they produce themselves, but with symbiotic relationships with organisms in their digestive system. They have, I believe, 4 stomachs. I think cattle have 4 stomachs. They have a very complex digestive system because cellulose as a material is very difficult to digest. We can't digest it ourselves. If we eat a lot of cellulose, that's another name for fiber in our diet. It runs right through us. It's good for us. It's healthy to have fiber in our diets, but we can't derive nutritive value from it. So if times get tough, we can't just go eat hay, but cows can. Just like with termites, they produce methane gas as well, and 90 megatons a year comes from cattle farming. That number would be a lot smaller if everyone was vegetarian or vegan. We didn't eat cows. Energy mining just beats that a little bit, 100 megatons. Particularly coal mining. Coal mines are, really what coal is, it's ancient compressed organic material, and often there was some level of anaerobic decomposition as it was being compressed. You get natural gas pockets underground, often interspersed with coal, and when coal is mined and brought out, these gas pockets often get opened up, and natural gas can be released into the atmosphere that way. So this was a huge issue in coal mining, when coal mining in Nova Scotia certainly was more of a thing, because people would, of course, have mines underground, and the gas, as it was released during the mining process, could form explosive mixtures, and you'd have explosions underground, and you could have collapses and other mining disasters as a result. So I believe this picture is Spring Hill coal mine, which has the famous Spring Hill mining disaster. So yeah, that's another way methane that's present underground, gets trapped, can be released. Waste treatment is another significant one. Again, there's all kinds of different ways we treat waste. And by waste here, I mean sewage. When you flush your toilet, everything goes out and ends up in these what are called settling pools. And these settling pools are just a place where the sewage, before it gets released into the environment, has a chance to decompose or compost, maybe is a nicer word for it. So it's put into these things. In some places, air is bubbled through this, which is actually fantastic because it helps aerate the water. It keeps it oxygenated so that if it's decomposition, it's going to CO2, which is a lot better than methane. But some places don't do that. Some places just left to sit still, and you get solids settle to the bottom, and you have the liquid sits at the top, and you have stagnation, and you have production of methane gas. I had a student in a previous year who had a job working for a waste or company, or I think probably a municipality in Ottawa. And what they were doing was going up and down the Ottawa River and finding places that weren't connected to a sewage system, but they had a septic system. They weren't connected to like a municipal, sewer. And what they were doing is cleaning out those systems and maintaining them for people so that waste didn't sort of build up, fill up the septic tanks, and then flow out into the river. So it was an attempt to clean up the river. But they would pump it into trucks, and then the trucks would settle it, would bring it into places like this. And she said that these settling pools were next to a big public park somewhere. And what they would do is, they'd let it sit for, I don't know, a month or 2 months or whatever the time was. And then when they were done, they would take the water, and they had these pumps that would shoot it into the air, this like huge spray, and they would spray it over the top of the park. And they used to do it sometime in the middle of the night. And it was, in terms of bacteria, E. coli, like enough time had passed that wasn't an issue anymore. It was sort of just like very rich fertilizer water at that point. And they'd spray the water, and the park, I guess, grew just like crazy because it was like constantly being fertilized. And then what you're left with at the bottom is a solid sludge. And that solid sludge also goes by the name of biosolids, which is a controversial product because biosolids, really, it's like human manure. And people say, well, why wouldn't you just use this on farm fields and so on? And there's a lot of, I guess, trepidation about that because people are worried that, if we're using pharmaceuticals or whatever, and that ends up in this sludge, and then you're putting it out on farm fields that we're growing food, is that going to be bad? I don't know what the state of the science is on that. I think they were using it in Halifax, actually, not for growing food, but for like parks and that kind of thing. I don't know. I remember there was a big campaign, though. People had these bumper stickers that said, like, say no to biosolids. And I don't know. It's an interesting thing. I haven't kept up with it, though. All right, so this is just a figure showing kind of where all the different sources for methane are coming from, split into natural and to human-generated. And the human-generated levels are, or contribution is higher than the natural contributions. And it goes up into the atmosphere, and then there's atmospheric removal. So at some point, it has a finite lifetime up there. It'll get up into maybe the stratosphere, react with ozone, or react with light and decompose. Eventually, it'll undergo a reaction and turn into CO2. That's its ultimate fate. So every gas has something called a global warming potential. Basically, this is a factor which tells you two things. One is how effectively this gas will absorb infrared light and send it back to Earth. The second thing is how long will it survive in the environment? How long does it survive in the atmosphere? So how much IR over its lifetime will it reflect back to the planet? Now, carbon dioxide is given a reference value of 1. So compared to carbon dioxide, how bad are all these other substances? You see methane, which is the number 2 most important gas, its number is 25, meaning 1 molecule of methane will have the same impact towards climate change as 25 molecules of CO2. So even though we produce a way more CO2 than methane, methane still is a very significant, of very significant importance because it has a much higher global warming potential over a 100-year horizon. See some other ones there. Nitric nitrous oxide, for example, is 298. That's way higher than carbon dioxide, but we produce very, very small amounts of this. So like, relatively speaking, it's not a big issue. If you go down this list, though, you can see some of these CFCs, like CFCs 11 and 12, have numbers in the thousands or tens of thousands. So there are compounds, and it's a good thing that we ban them, except after we ban them, we replace them with HFCs. And so you see there's an HFC down there on the list with a value of 1,430. So these things are bad too. They absorb infrared light. They have polar bonds that change their polarity through a vibration. So they can absorb infrared light and send it back down. And these things typically have very long lifetimes in the atmosphere. So those combine to give these very high global warming potentials. So we wouldn't really have to be producing a lot of these substances before they become a problem very quickly because of this high global warming potential that they have. So we're not yet at the point with any of those that they're contributing to, you know, more than 1% or 2, but we don't want to get there either. A few more questions. Which of the following is not a name for CH4? Propane, marsh gas, methane, natural gas. The answer is propane. Propane is a different chemical structure. It's got 3 carbon atoms. It's C3H8, and that's the gas we would burn in barbecues typically. So, climate change is definitely, probably the preeminent, most important, most severe environmental problem that we are facing right now. Like large-scale environmental problems before it, that almost seem like a distant memory sometimes now, like, you know, acid rain or ozone depletion. This idea of climate change seems to be going through the same sort of steps. First step, recognition of the problem. Second step, I think we inserted last class, convincing the public that this is an actual problem we should be concerned about. Then technological solutions, and then, of course, political action. And those don't have to happen in sequence. They can happen together. And I think they are all happening together. First one is technological solutions. And this is a huge area of growth right now, technological solutions. So, of course, one of the biggest sources of carbon dioxide is combustion engines in cars. If we can replace combustion engines with electric motors, that will solve that problem. And as we see, electric cars is booming right now. It's the rate of growth in that sector is enormous. And it's nice at Acadia, we have those charging stations now down by the gym. I've never seen a car plugged into one, but who knows? In 5 years, people will be fighting over them, hopefully, right? You're seeing a company like Tesla, they grew by 750% last year, I believe. When I say they grew by 750%, I mean share price grew by 750%. I don't know what their sales did. But you're seeing every major company, car manufacturer, get on board with this. Solar power, you're seeing more and more. This is a picture of a solar farm in Florida, just outside Disneyland. And I forget the stats. I think they have this solar farm and possibly some other ones in development. You can see how big that is relative, like there's a road running beside it. You can see there's a bus on the road. This power plant, the other solar power plants, I think they supply, I forget the fraction, some significant fraction though of the electricity that is drawn by the parks. So they're on a mission to become carbon neutral, right? Which is great. And obviously there's the branding here of Mickey Mouse, so they maybe could squeeze in a little bit more panels if they went, you know, to the dead areas here, but okay. Now it looks like Mickey Mouse's earrings. There are lots of potential solutions. There's a whole process called carbon sequestration where people are trying to prevent carbon dioxide from getting into the atmosphere to begin with. This is very difficult to do on the scale of individual vehicles, but if electric vehicles can replace gas-powered vehicles, that's not a problem anyway. So the thinking is, if you have power plants that are producing large amounts of CO2 in a very localized area, can we extract the carbon out and don't let them into the atmosphere right to begin with? And so there's all kinds of different solutions that are being proposed. Unfortunately, most of these at the moment are very either inefficient or very expensive, or require electricity themselves to operate. So if you're producing electricity to then burn that same electricity to then capture the CO2 from the initial, you're not getting ahead, right? So you have to capture the carbon in a way that produces less carbon than you're capturing, which is, I think, so far the biggest technological issue. I remember thinking about this a while ago, thinking, let's say you wanted to invent something that could capture carbon dioxide out of the air. What design features would you want to put in? And it's like, well, you'd want it to not operate on electricity, first of all. You'd want it to be, let's say, solar powered and self-sustaining. You'd want it to be independent. You wouldn't want it to have to be connected to a grid. You'd want it to have no moving parts because you don't want to have to maintain it. You want it to be cheap, right? You want it to be, what are some other things, right? You want it to last. You don't have to physically have to go in and do any work on it or maintenance. You want it to be simple to install, cheap to produce, all these kinds of things. And it struck me all at once that what I was describing was a tree, right? Like a tree requires no maintenance, cheap to install, no moving parts. They don't, well, I guess if there's a hurricane, they can break, but they extract CO2 out of the air. They're solar powered. They're all of those things. So really, an important way to fight climate change, I think, and this has to happen on a huge scale, is plant more trees. And you're seeing places do this. India, I think in the last couple of years, have committed to plant some, I don't know how many billions of trees, and they're well along their way towards that goal. Lots of other benefits besides just capturing carbon dioxide to doing that as well, in terms of animal habitat and so on. Political action is the other element here, right? Political action began as early as the early 90s with the UN Framework Convention on Climate Change, where this is an international agreement where countries are starting to come together to discuss this problem. And 92 was kind of a long time ago, right? That's like 30 years ago. And things have gotten a lot worse in terms of how much CO2 we're putting out since 92. But already at that point, people were aware of the issue and were trying to do something about it. A more substantial agreement came in 1997 with the Kyoto Protocol. The Kyoto Protocol was done in Kyoto, Japan. And of course, this was a plan to scale back on the amount of carbon dioxide that was being emitted. This is a map of the world. All the green countries are ones that agreed and signed on. The red countries are the ones that said no thanks. And the one that wouldn't sign at this point was the US. And who was president then? Was this George W. Bush? Might have been. But the US wouldn't sign on, and this was a major issue because the US was, at that point in time, the #1 producer of carbon dioxide. So if the biggest fish isn't going to play ball, it undermines the efforts of anyone else to really make serious headway in this particular place. This is a picture in 2012. We can criticize the US at that point for not joining, but Canada signed on and then just did nothing. So we signed on to the Kyoto Protocol and then just continued to emit away, continued development of the oil sands, all these other things that were producing the CO2. So is it better just to say no thanks, or is it better to say okay and then just, it's like, is it, if someone invites you to a party, is it better just to say no, I can't make it, or to say yeah, I'll be there and then just not show up? Because that's kind of what Canada did. And Canada eventually pulled out, and Stephen Harper pulled us out in 2011 or 12. And at that time, they got a lot of criticism for that, but we weren't even listening to it either way. So I guess you could argue they were being honest. One argument against the Kyoto Protocol at that time was that developing nations, which are now the major producers of CO2, like China, had little to no restrictions. They had much less strict restrictions than the Western countries did, which, I mean, I guess you could rightfully argue that the emissions per person in countries like China and India are still way lower than they are in the West. Total is higher. And so that didn't sit right with some people. Inconvenient Truth was a book and then documentary about, which I think this actually played an important role in bringing into the public kind of understanding the importance of climate change and what was going on. And this was a project by Al Gore and others. Nobel Peace Prize to recognize these efforts went to Al Gore and the Intergovernmental Panel on Climate Change in 2007. So there's starting to be some, political movement. Some certainly public perception among certain groups was quite high at this point in time. Of course, people were looking around saying, yeah, this is great, like, let's stop global warming, but the technological solutions weren't there. So, I mean, it's great to say, okay, let's stop producing CO2, but how are you going to get around? How are you going to heat your house? How are you going to do all these things without really just blowing up the economy? And the reality is we've grown this economy, which is supporting 7 billion people. It's not practical just to expect, because people need to eat. People need to do their jobs and get around and travel and live. Yes, we can cut back on the worst behaviors that are producing CO2. Like, for example, can you get rid of your huge Hummer vehicle and switch it for like a more economic car? Yeah, there's those sorts of things. But yeah, right? You can't suddenly just cut down to zero because the solutions weren't there. The technological solutions, which are in development now, things like solar energy, electric cars, and so on. 2010, basically all of the major national science academies signed on. So you see the Royal Society of Canada is listed there. They agreed global warming is happening and anthropogenic, which means caused by human beings. Then we had the Paris Agreement, right? Paris Agreement was kind of, it seems like, and I'm not an expert on all of this and how it exactly went down, but it seems almost like a recognition that there was improvements needed in the Kyoto Agreement, and it was sort of replaced or superseded by the Paris Agreement, which actually famously had sign-in from countries like the U.S., although Donald Trump pulled the U.S. out of the Paris Agreement. Biden just recently put them back in. So Paris Agreement's currently a go. There is a lot of activity now, a lot of action by certain governments to reduce the amount of carbon dioxide that's being produced. So Norway has vowed to completely ban gas-powered cars by 2025. And this is actually data from last month in 2020. This is new vehicle registrations in Norway, and the green ones are the percentage, 75.2, which are electric vehicles. So they're well on their way to meeting that goal by 2025. We're nowhere near that in Canada, right? And this is, in part, every country is a little bit different. The needs are a little bit different. Norway is a much smaller country by population and far richer as a result of North Sea oil. So they were enriched by fossil fuels, and I guess Canada is to a large extent as well, so I guess we can't claim better than that. But around 7.7%, I guess around 18%, if you add those two together, are oil, primarily vehicles, with 7.1 being hybrid, so half and half. France has agreed to shut down all coal-fired power stations by 2021, and that's this year. So I guess that's going to be happening. This pledge was made in 2018. I don't know where they're at with this pledge, but France is interesting. Actually, they have been a low emitter in terms of electricity production for a long time, and that's because I believe somewhere above 70% of their electricity comes from nuclear plants. So they're a huge nuclear power producing country. Canada, we are making efforts, it seems a little bit more each year. One thing that Canada has put in is carbon pricing, which has been certainly not universally loved. But what this means is there's a tax on carbon pollution, which causes industries that produce a lot of CO2 to then have to pay more, and industries that produce less pay less. So this is an attempt to use economics to persuade businesses and so on to reduce the amount of CO2 we produce. I don't know what the amounts are right now in Nova Scotia. Like if you go and buy $100 worth of gasoline, what fraction of that is actually due to carbon pricing? It's a little bit different in every province. But anyway, this is an effort by the Trudeau government, which I believe the plan is to step this up in the future. So using taxation, economic tool, which I guess you could argue is a technology, right? It's not an obvious thing like a vehicle or a solar panel, but same sort of idea. So yeah, Donald Trump pulled out of the climate agreement, the Paris Climate Agreement, but Biden brought it back in. So yeah, this is still going. GM claims that almost all their vehicles that they'll be producing will be electric by 2035. So that's not as ambitious as Norway, but this is big, right? They're the biggest auto manufacturer in the world. If this happens, just think about it, right? In 15 years, it could be the end of gas-powered cars. Because if GM is willing to do this, which is an American company, you can bet that Toyota and all these other manufacturers will be doing this as well. So this is great news. It seems like the technological solution for vehicles, and of course this creates all kinds of new supply chain issues and so on, but lots of opportunities as well. And Tesla is of course a big player currently in the electric car market, and they are collaborating with exactly one academic research team, and that's out of Dalhousie University. So Nova Scotia is a player in the EV scene as well. Solar electricity has been a huge area of research. I know my personal area in photochemistry, there's a lot of research being done on these things called dye-sensitized solar cells. And I remember when I first did my PhD back in like the early 2000s, where the state of things was then and where it is now. Going kind of hand in hand with this is the development of organic light emitting diodes, OLEDs, which are used in modern cell phone screens. They're like the reverse of a solar cell. A solar cell absorbs light and turns it into electricity. The OLEDs take the electricity and turn it into light. And the materials they use are actually a little bit similar. The device design's a little bit similar. And OLEDs are great because they're very efficient. They don't use a lot of electricity to produce the light. So the solar cells are doing the same thing in reverse. Solar costs since 2010 have decreased by a factor of 5, which I'm sure was at least a factor of 5 cheaper than it was in the year 2000. So right now, solar is as competitive as any other technology. And if this continues to drop, it would never make sense. Like France saying, yeah, we're going to get rid of all our coal-powered plants. Why would you even have them if you can get energy more cheaply using solar means? And so this really, I think, is another technological solution, a very obvious technological solution, especially when you have areas in places like the US with deserts where you have large amounts of land that get a lot of annual sunlight. You even think around here, you could cover roofs. If you could do it cheaply, the amount of electricity you could produce doing things like that. So I feel like we're, like over the hump for climate change when it comes to technological solutions. And hopefully the technological solutions just continue and just replace the polluting alternatives that are going right now. It's actually interesting because like for me teaching this class and teaching this particular unit, I would say like this is the most hopeful presentation I've ever been able to give on this. Because if you looked at this like 5 years ago, it looked super bleak, right? And not to say that, okay, problem solved, dust our hands off and move away. But I hope when I'm like an old man and I'm teaching this course and I'm doing this unit on climate change, it's like the unit I just gave on acid rain, right? Or on ozone. Like it's a problem. We dealt with it, came up with technological solutions. It was a bumpy road, not to say it was smooth and everyone was on board right away or that we're there now. But hopefully, there's hope that this is a tackleable problem. And there seems to be, for the first time, I've been following the issue, real traction. And like a real obvious solution you can point to. So question 10, what is the current international agreement to tackle climate change known as? This is the Paris Accord. It's not the Tokyo Treaty. It's not the Montreal Protocol, and it's certainly not the Seattle Mariners. Although there's a new NHL team coming. Seattle, you know what it's called? It's the Seattle Kraken. Which is, I don't know. Completely unrelated to what we're talking about. Great. That's it. We are done. We are finished with this unit, and it's 3:22, and there's no way I'm going to be starting a new unit right now. So, another one to check off. That means 1 week from today, the unit assignment is going to be due for this particular unit. So please finish it right now while you're watching this. But I'll change the due date that's on that to reflect the actual due date. So usually what I do when I first post them is I have to pick some due date, and when I don't know what it is, I just put it up, and then once I know when the last class finishes, I just revise it at that point. So if you see a due date in there that doesn't seem to make sense, it's because I haven't revised it yet, but I think everything at this point is up to snuff. Great. So thanks everyone. I am continuing dealing with emails and so on related to the first assignment. And so I'm not 100%. I can't dust my hands off quite yet and say that I'm done with that assignment, but I'm certainly getting there. And goodbye.